Okay, good morning everyone. So today we're going to discuss about water potential, solid potential and pressure potential. Okay, so water potential can be represented with a psi symbol that look like a trident. Okay, how do you write this psi symbol? Very easy, U and then L. So water potential is the tendency of water to move from one area to another area. Okay, usually water moves from a higher water potential to a lower water potential region. Okay, or simply you can say that water potential is the tendency of water to move water potential is the tendency of water to move down the water potential gradient. Okay, now water potential of pure water is 0 kilopascal or 0 megapascal or 0 bar. Now basically a cell, okay, or an environment with a more negative water potential, okay, meaning to say like negative 10 kilopascal, negative 20 kilopascal instead of 0. Okay, so the cell or environment that has negative water potential will draws in water. Okay, but again this condition depends on the solid potential and pressure potential. Now osmotic or solid potential, okay, trident or psi, then S here, S huruf kecil lah. So ini maksudnya ialah solute potential or osmotic potential. Ini ialah defined as component of water potential due to the presence of solutes. Okay. Now the effect of this solid potential, right? Solid potential always will reduce the water potential because solid molecules reduce the movement and energy of water molecules. This is because solutes, they like to be attracted to the water. Water moves freely, right? Water molecules, okay, in a pure water, they move freely. These water molecules move freely because of the kinetic energy that they possess. But when we add in solutes into a pure water, what happens? This solute will bind or attach to these free moving water molecules. So when the solute bind with these free moving water molecules, what happens? These water molecules will not be able to move freely. So because of that, the water potential of that solution or that environment will decrease. Usually it will decrease. Okay, again it depends on calculation. Okay, depends on calculation. Calculation you will do afterwards in your exercises. Now solid or osmotic potential, okay, you know already is defined as trident S, okay, and the formula is given as negative I CRT. You have to memorize this formula. It won't be given in the exam, but the value each of these subject will be given. Okay, so I is the number of particles the molecule will make in water. Okay, usually sucrose or glucose, the value of I is 1, while sodium chloride or salts, okay, the value of I is 2. Okay, usually, unless stated in the question. C is the molar concentration, okay, and R is the pressure constant. Okay, pressure constant, which is 0.0831 liter bar per mole, okay, Kelvin. Next, T is the temperature in Kelvin, okay, of the solution. So temperature in Kelvin, how do you convert degree Celsius to Kelvin? Whatever the figure in the degree Celsius form, you just add in with 273. Okay, so kamu akan dapat temperature in Kelvin. So this is the formula to calculate solid potential. Okay, now pressure potential on the other hand, okay, like trident and P. Okay, so pressure potential is defined as component of water potential due to the exerted pressure. So whenever a pressure is being exerted, okay, that is pressure potential. Now, pressure can be, please take note, bear in mind, pressure can be exerted two ways, positive and negative. Positive means to say we apply the pressure. Negative means we take out the pressure from an environment. So the pressure potential will be negative. So the effect, right, of pressure potential is pressure potential will increase the water potential value because pressure increases the movement and energy of the water molecules. This is true when pressure is being applied, right? But when pressure is being taken out by example suction, for example, a suction, I will further explain about the suction later on, right? The pressure potential will decrease, or the pressure potential will be negative in value. And when pressure potential is negative in value, it will influence the value of the water potential, where the water potential can be either remains in positive or be lowered into negative value. So increased pressure, right, will give positive C. Okay, not C, sorry. Okay, increased pressure potential will give positive increased pressure will give positive, sebetulnya ini nih salah type symbol. Alright, sorry for the salah type symbol. Okay, ini baru betul. Alright, increased pressure, okay, or when pressure is being applied to an environment, okay, usually this will give positive pressure potential. Okay, and suction pressure, like what I explained earlier, okay, will give negative pressure potential. Right, now positive pressure potential and negative pressure potential, both of these factors will influence the total water potential of a solution or an environment. Okay, now pressure potential in plant cell is always positive due to the turgor pressure that is counteract the solute potential of the plant cell. Okay, now if you're wondering the difference between turgor pressure and pressure potential, okay, to cut short, when water diffuse into the plant cell, okay, by osmosis, okay, this cytoplasms here, okay, will gain pressure. Okay, when water diffuse into the plant cell by osmosis, this cytoplasm will gain pressure. That is the pressure potential. Okay, because the water already goes in, and then that will give the cytoplasm of the cell pressure. Okay, now when the cytoplasm has pressure, what happens? Okay, the component, the organelle of the cell, especially the vacuole of the cell, will exert pressure to the cell membrane, and in turn that the cell membrane will exert pressure to the cell wall of the plant cell. Now this pressure, okay, is being exerted, okay, against the cell wall is the turgor pressure. Right, now osmosis, okay, it is the diffusion of water across a semi-permeable membrane due to the concentration differences. Okay, and osmotic pressure is the force needed to stop osmosis. Okay, osmotic pressure is the force needed to stop osmosis. Now, tonicity, okay, is the ability of a surrounding solution to cause a cell to gain or lose water. Depends on concentration of solutes that cannot cross a membrane relative to that inside the cell. If there is a higher concentration of non-penetrating solutes in the surrounding solution, water will tend to leave the cell and vice versa. Okay, solids ini, they are not necessary boleh masuk ke dalam cell. Okay, if the number of the solutes inside the cell is high, what will happen? The water from the environment will diffuse into the cell via osmosis. Okay, because the solute inside the cell, right now, take an example like this one. Okay, the solute inside the cell, they are so large that they can't simply move out from the cell. So the solute will remain inside the cell. Okay, and these solutes are non-penetrating solutes because they are big in size and they can't simply move out from the cell. So what happens? Water will diffuse into the cell by osmosis. Okay, vice versa. Meaning to say, if the cell is being placed in an environment which has higher solute potential, what will happen? Okay, the solute from the environment cannot simply move into the cell. So what will happen? Water from the cell will diffuse out from the cell via osmosis into the surrounding environment, because you know water, right, diffuse from a region of higher concentration to a region to the lower concentration. Okay. Now, isotonic solution is a solution that have identical concentrations of solid molecules and same osmotic pressure. Okay, itu ialah isotonic solution. Dia mempunyai concentration of solid molecules identical and same osmotic pressure. Now, in an isotonic solution, water will diffuses into and out of the cell at the same rate with no change in cell size. Okay, when we have animal cell and plant cells being placed into an isotonic solution, okay, there is no change in the cell size. Okay, because water diffuses into and out of the cell at the same rate. So meaning to say there is no net movement of water, or there is no net gain or loss of water. Again, in the previous video, I spoke about this no net movement of water. No net movement of water, it doesn't mean that there is no movement of water molecules, but no net movement of water means the water that move out from this cell, for example, is the same with the rate of the water molecules diffuse into this cell. Okay, pergerakan keluar dan masuk air itu sama. No, I shouldn't say pergerakan keluar masuk. I should say the diffuses of water molecules by osmosis into the cell is equally the same with the rate of diffusion of the water out from the cell via osmosis. An animal cell, okay, fares best in an isotonic environment. So meaning to say an animal cell has the best condition in an isotonic environment. Okay, plant cells, however, they are flaccid in an isotonic environment. Okay, plant cells, they are flaccid in an isotonic environment. Do keep that in mind, right? Now, hypotonic solution, okay, is a solution that have solid concentration or osmotic pressure that is less than that of the solution which it is being compared. In a hypotonic solution, water moves into the cell and pressure is applied to the plasma membrane until the cell ruptures. This is correct for all cells that is lack of cell wall. Alright, this is true for cell that is lack of cell wall, like for example your erythrocytes. So what happens? Water enters the cell, okay, due to osmotic pressure from the higher solid concentration in the cell. So when this cell, for example, this erythrocyte is being placed or put in a hypotonic solution, okay, this cell has solute, right? And the solute potential inside this cell is higher compared with the hypotonic solution. So what happens? Water from the hypotonic solution will diffuse via osmosis into the cell. Okay, and this may cause the cell to burst if the cell is continued to be placed in that hypotonic solution. Okay, and when that cell bursts, it is called the cell undergoes lysis. So an animal cell may burst, right? The strong cell wall of plant cells can withstand the hydrostatic pressure to keep the cell from rupturing. So it's a different condition for plant cell. So plant cells, however, they are turgid or firm, okay, and generally healthiest in a hypotonic environment. Okay, so animal cells or cells that do not have cell wall or lack of cell wall, they are best in the isotonic solution. But cells with cell wall, like plant cells, they are the best in a hypotonic solution or hypotonic environment. Okay, so in a hypotonic solution, what happens? The vacuoles will fill with water. Okay, next turgor pressure develops, okay, and chloroplasts are seen next to the cell wall. Now, hypertonic solution, okay, is a solution having solid concentration or osmotic pressure greater than that of the solution which it is compared. So hypertonic solution means, say, it is a solution that has higher solid concentration or solid pressure compared with the cell. Now, in a hypertonic solution, water moves out of the cell, okay, or water diffuse out from the cell via osmosis, causing the cell to shrivel, or any cell that is lack of cell wall to shrivel. Okay, and other word for shrivel is crenation or crenated. So in a hypertonic solution, as you can see in this diagram here, all right, hypertonic solution means to say the solid potential is higher, okay, in the solution compared with the solid potential in the cell. So water will diffuse out by osmosis from the cell into the hypertonic solution. Now, in plant cells, okay, the vacuoles lose water, all right, because the water from the vacuole will diffuse out, okay, out by osmosis into the hypertonic solution from the vacuole. So in plant cells, vacuole is water, the cytoplasm shrinks, okay, the cytoplasm shrinks, and the shrinking of this cytoplasm we term as plasmolysis. Okay, or the cytoplasm undergoes plasmolysis, and chloroplasts are seen in the center of the cell. Okay, now I need to add in here, I need to repair here, water diffuses out of the cell via osmosis. Okay, now I need to stress out here the diffuses via osmosis, because this involves movement of water, right, through a semi-permeable membrane. And usually candidates in the exam, if you write the water move out of the cell tanpa ada perkataan diffuse atau osmosis, salah. Okay, so water diffuses into the cell okay, so please betulkan di modul kamu, water diffuses via osmosis into the cell. Okay, yang sini in and out the diffuser. Alright, ini pun betulkan juga. Okay. Now, a quick recap. Okay, identify the movement of water of each solution. Now, this is a U-tube that has pure water. So the water potential of this water in this U-tube will be 0 Pascal. Betul kan? So now when we add, okay, when we add solute, all right, to the right arm or right side of the tube, these dots here represent a semi-permeable membrane. Okay, semi-permeable membrane. So when we add solute here, what happens here? This right arm will have lower water potential because of the solid potential. Solid potential, they are always negative in value. Okay, solid potential. So solid potential will decrease the water potential. So the water potential in this region will be lower compared with this region. So adding solid to the right side lowers the solid potential. Sebenarnya water potential nih, right side lowers the water potential here. Okay, causing water to move to the right side of the tube. Okay, so ini water potential dia lebih besar daripada sini. Sini 0, sini negative. So water will diffuse by osmosis to the right side. Okay, now what happens if we apply pressure here? So meaning to say the pressure potential here will be positive value. Okay, now bila pressure potential sini positive, okay, water potential di sini juga lebih besar. Okay, so bila water potential sini lebih besar daripada sini, okay, the water from this region or from the left arm of the U-tube, okay, will diffuse by osmosis to the right arm of the U-tube. Now, when pressure is being sucked out, okay, from this left arm of the U-tube, so the pressure potential here will be negative. When pressure potential here is negative, the water potential here will be negative as well. Okay, so when the water potential here is negative and the water potential here on the other side is greater, so water will diffuse by osmosis from the right tube to the left tube. Okay. Now, I forgot to mention, all right, basically water potential, okay, is calculated by, water potential can be calculated by the total of the pressure potential and the solid potential. The sum of the pressure potential and solid potential will give you the water potential of that water or that solution. Okay, now let's say for this example here, okay, the right side here, the right arm here, right, has only pure water, so obviously the water potential will be 0 megapascal. And on the left arm here, right, you can see, all right, 0.2 molar. The solution here, concentration is 0.2 molar. So meaning to say this solution here, it has water as well as solutes. Okay, but no pressure, because pressure is not being applied or sucked out. So pressure potential equals to 0 megapascal. Solid potential, let's say, because the presence of these solutes, okay, and then the 0.2 molar, and then calculated by the I, then the R, and then the temperature, let's say we get the solid potential as negative 0.46. So the water potential in this region calculated as 0 plus negative 0.46. Total we get negative 0.46 megapascal. So apparently the water potential in this region, right, this left arm, is lower compared with the water potential on the right arm. So water will diffuse by osmosis from the right arm to the left arm. Sebab because the water potential in the right arm is greater than the left arm. Now another scenario here where positive pressure, okay, or pressure is being applied, okay, to this left arm. Okay, now this is a continuation from the previous question here. Okay, so the pressure potential, let's say the pressure potential is being applied is is 0.46 megapascal. Okay, let's say example, the pressure potential that is being applied here is 0.46 megapascal. Okay, and we know already from the previous condition here, the solid potential is calculated as negative 0.46. So what is the total water potential here, or what is the water potential here? That will be 0.46 plus with negative 0.46, which will give you 0 megapascal. So the water potential on the left arm and the water potential on the right arm both are equally the same, which is 0 megapascal. So there is no net movement of water, meaning to say pergerakan air daripada kiri ke kanan ke kiri adalah sama rata. Okay, now again continuation, okay, from the previous picture. Okay, now let's say the pressure is being increased. The pressure is being increased. Okay, so the pressure potential 0.50. Let's say lah, alright, the pressure is increased and the value of the pressure potential is 0.50. Now the solid potential remains negative 0.46. So now if we recalculate the water potential here in the left arm of this U-tube, we will get 0.14 megapascal. Okay, and on the right arm, which is still has only pure water, okay, and so the water potential will be still 0 megapascal. So you can see that the left arm here, all right, has higher water potential compared with the other arm. Okay, so what will happen to the movement of water? Okay, so the water will move from the left arm to the right arm. Okay, higher water potential to a lower water potential. Okay, so the water will diffuse via osmosis from the left arm to the right arm. So left arm ini dia punya water potential lebih besar, so air akan bergerak arah macam ni. Now what happens, right? Same condition, okay, terbalikan sikit. Okay, ni terbalik. Alright, terbalik. Or never mind. Okay, new condition here. Okay, new condition here. Let's say on the right arm, alright, no pressure is being applied, and then the solid potential is given as negative 0.46. So the water potential in this right arm would be negative 0.46 megapascal. Betul kan? Because solid potential campur dengan pressure potential. Right, so 0 plus negative 0.46, you get negative 0.46. Now let's say on the left arm here, what happens? Pressure is being suctioned. There is a suction of pressure here. Okay, there is suction pressure. Oh, I'm so thirsty. Okay, there is a suction pressure here. Okay, there's suction pressure. So suction pressure is negative pressure potential, and let's say lah, right, the pressure potential here is negative 0.50. Right, and this solution here consists of only pure water. Okay, so solid potential is 0. So the water potential in this region will be negative 0.50 plus with 0, you get negative 0.50. So the right arm apparently, okay, has bigger water potential, which is negative 0.46 compared with the left arm, which has slightly lower water potential, which is negative 0.50. Okay, negative 0.46 lebih besar kan daripada negative 0.5, right? So what happens? Water will diffuse by osmosis from the right arm to the left arm. Okay. Now, water potential of a plant cell in a solution. Now, this is the last part for today's discussion. Okay, water potential of a plant cell in a solution. Now, yang ini, okay, you must be identify what happens to a plant, okay, especially plant cell, when they are being placed in a solution. Okay, you must be able to calculate the water potential and what happens to the movement of the water. Okay, the water will diffuse in which direction, like what I explained earlier. So now, the water potential of a plant cell in a solution, okay, depends on the amount of solutes, water content, and turgor pressure. So water potential calculated as pressure potential plus with solute potential, or the sum of pressure potential and solute potential, like what I've already explained. Now, when the plant cell is not immersed in a solution, right, pressure potential always equals to 0 unless pressure is being applied or sucked out. Okay, now, so when the plant cell is not immersed in a solution, pressure potential is 0. So water potential will be equals to the solute potential, right? If the plant cell is not immersed in a solution. Oopsie. So now we have 1, 2, 3, 4 conditions here. All right. Now, yang first one ini, okay. So like what I've already explained earlier. Example, all right, in this U tube here, pressure is not being applied, so the pressure potential is 0. Let's say, and then the water here is already be added with solute. So this is a solution here, and given the solute potential is negative 1 megapascal. So the water potential in this right U tube will be negative 1 megapascal, and on the left side the water potential, since it has only water without any pressure and such thing like that, so water potential is 0. So the water will move, right, or diffuse from the left arm to the right arm via osmosis. Betul kan? Okay, ini pun sama juga bila ada pressure, so I won't discuss about this. Now, what happens when a plant cell is being immersed in this solution here? Okay, so this pure water, okay, has 0 megapascal water potential. Now, this plant cell is a flaccid cell, right? Okay, it's a given flaccid cell is being immersed in a solution or water, a pure water. So, given here the flaccid cells, all right, the pressure potential is 0, okay, and the solute potential is negative 1. So, when we calculate the water potential, we will get 0 plus negative 1, we will get negative 1 megapascal. So the pure water has 0 megapascal water potential, while the water potential in this flaccid cell is negative 1. So now, macam mana dengan pergerakan air itu? So the water molecule will diffuse into the flaccid cell via osmosis. Betul kan? Sebab water potential pure water lebih tinggi daripada water potential flaccid cell ini. Now, what happens when we have a turgid cell? We immerse this turgid plant cell into a pure water solution. So, pure water has 0 megapascal water potential. Now, a turgid cell, let's say lah, all right. This turgid cell has a pressure potential of positive 1.0 megapascal. Okay. And then the solute potential inside this turgid cell is negative 1.0 megapascal. So we calculate the water potential of this turgid cell. 1 plus negative 1 will be 0 megapascal. So is there any movement of water? Yes, there is no net movement of water, meaning to say water diffuse into the turgid cell via osmosis is the same with the water that diffuse out from the turgid cell via osmosis, or the rate of water diffused into the turgid cell is the same as the rate of water diffused out from the turgid cell. Okay, all right, so that's it for today. Okay, thank you, bye.